Hello, future engineers. Welcome to my YouTube channel. If you're still new to my channel and you like what I'm doing, please don't forget to share my videos to your friends and to your friends' friends. That's the only way you can help me and help your friends discover my channel and to keep me going, refreshed, and inspired. Also, don't forget to subscribe if my videos are helpful to your studies. So for the restrained beam shown, compute the fixed moments in two ways. So this is the last example. Uh, the loading is challenging, though in reality it will not be. But this is for mastering the concept on computing fixed moments, especially the basic one, which is construction of moment diagram by parts. So let's select B as our moment center, and let's consider fixed moment at A positive as shown, and the reaction RA times 10, so 10 RA. Then for this trapezoidal loading, let's divide this into rectangular and triangular. So for the rectangular, 15 times 4 times 2, the moment is 120 and it is second degree curve. So this loading is replaced by a 120 couple and 15 times 4, 60 kilonewton load. So the couple is then transmitted to be 120 also. Then 15 times 4 is 60. The moment of this 60 kilonewton load at B is 60 times 4. So we have triangular moment diagram 240 further. Then for the triangular loading, the intensity is 15. So the moment here, its third degree is 1/2 of 4 times 15 times 4/3. And it is third degree. The value is 40. Then this triangular loading is replaced with a couple counterclockwise. So let's transmit the 40 kilonewton meter couple to B as shown. Then the equivalent loading is 1/2 of 4 times 15. So that's 30. So the moment at B is 30 times 4, so 120, represented by this triangular moment diagram by parts. Then for this trapezoidal loading here, we fill this gap to make it rectangular and counter it with an upward triangular load of intensity 9 because 30 minus 21 is 9 as shown. So therefore for the equivalent couple, it is third degree here. 1/2 of 3 times 9 times 1, it is third degree, positive 13.5. So this triangular loading is replaced with a couple of 13.5, which is clockwise, and the force is 1/2 of 3 times 9, which is 13.5. So the couple is transmitted further, 13.5. Then the load equivalent upward force is 13.5 times 1. So we have a triangular moment diagram with intensity 13.5, or moment at B is 13.5. Then for the rectangular loading, 30 times 3 times 1.5, it is second degree. And the value is 135. So it is replaced with a couple of 135 counterclockwise plus the force. So let's transmit the couple to B, second degree, 135. Then the force is 30 times 3, 90 times 1. So we have 90 triangular value. So that's it. This is the complete moment diagram by parts. So first equation, AI theta AB equals 0. So 10 MA plus 1/2 of 10 times 10 RA. Then equals, let's begin with this second degree spandrel, 1/3 of 4 times 120. Then we have 4 times 120 for this rectangle. For this triangle, 1/2 of 4 times 240. For this third degree curve, 1/4 of 4 times 40. For this rectangle, 4 times 40, the area. For this triangle, 1/2 of 4 times 120. Then minus for this spandrel, 1/4 of 3 times 13.5. For this rectangle, minus 13.5 times 1, or 1 times 13.5. For this triangle, minus 1/2 of 1 times 13.5. Then plus for this spandrel, 1/3 of 3 times 135. 1/3 of 3 times 135. For this rectangle, 1 times 135 plus 1 times 135. And lastly, for this triangle, 1/2 of 1 times 90. So simplifying, 10 MA plus 50 RA equals 1844.625. Call that equation 1. Then same terms, we just multiply this by the moment arms. So AI division of B relative to tangent at A equals 0 also. So 10 MA times 5 plus 50 RA times 10/3 moment arm triangle 10/3 at B. Then this distance is 4/4, or 1 plus 4. So the moment arm, or the distance of the centroid of this curve from B is 5. And the area is 1/3 of 4 times 120, that is equal to 160. So equals 160 times 5. For the rectangle, 4 times 20, 480. Moment arm is 2. This is also 480 for the triangle, and the moment arm is 4/3. 480 times 4/3. For this third degree curve, the area is 1/4 of 4 times 40, or simply 40. And this is 4/5, or 4.8. Distance of its centroid from here is 4/5, or 0.8 plus 4, so 4.8. So plus 40 times 4.8. Then for the rectangle, the area is 4 times 40, or 160. Moment arm is 2. For this triangle, the area is 2 times 120, 240. Moment arm is 1/3 of 4, or 4/3. Then minus this third degree curve, 1/4 of 3 times 13.5. This one, that's 10.125. And the moment arm is 3/5, 0.6 plus 1, so 1.6. So minus 10.125 times 1.6. For this rectangle, 1 times 13.5, the moment arm, the area is 13.5, and the moment arm is 0.5. Then for this triangle, the area is 6.75, and the moment arm is 1/3. So minus 6.75 times 1/3. For this secondary curve, the area is 135. This distance is 3/4, 3 meters over 4, 0.75 plus 1, so 1.75. So plus 135 times 1.75. For the rectangle, the area is 135, moment arm 0.5. And lastly, the area of the triangle is 45. This one, 45, moment arm 1/3. Simplifying, 50 MA plus 500/3 RA equals 3525.55. Call that equation 2. Solving these two equations simultaneously, we get MA, friction moment at A, negative 157.392 kilonewton meter. RA is equal to 68.3709 kilonewtons. Therefore, the moment at B, or friction moment at B, is 10 RA, 10 times 68.3709 plus MA, which is negative 157.392, minus 120, minus 140, minus 240, minus 40, minus 120, minus plus 13.5 plus another 13.5 minus 135 minus 90. So MB or fixed moment at B equals negative 191.683 kilonewton meter. For the second method, let's have a strip application of fixed moment A negative P AB squared over L squared, but by integration. So imagine that this is X, therefore W minus 15 as to X equals 15, 30 minus 15 is 15 as to 4. Since 15 over 4 is 3.75, the height of the strip intensity here is 3.75x plus 15. Therefore, the differential force is 3.75x plus 15 dx. For the right part, that's the strip. So this is W minus 21 as to, let's call this distance x from the right. Then W minus 21 as to x equals 30 minus 21 is 9 as to 3. Therefore, the intensity here is 3x plus 21. So the differential force is 3x plus 21 dx. Fixed moment A, therefore, is negative integral of quantity 3.75x plus 15. A is 2 plus x. B is, this is 8 minus x. 8 minus x squared over 10 squared. So negative integral from 0 to 4, 3.75x plus 15 dx, 2 plus x times 8 minus x squared all over 10 squared from 0 to 4. And here we have plus minus integral of 3x plus 21 dx. The distance of this strip from the left is, this is 2, 6, 9, 9 minus x. Then its distance from the right is x plus 1. So integral of 3x plus 21 dx times 9 minus x times x plus 1 square over 10 square, 0 to 3. So 3x plus 21 dx, 9 minus x times x plus 1 square over 10 square, 0 to 3. The value of this integral is negative 118.08, while this integral is negative 39.312. Combining, fixed moment A equals negative 157.392. It's the same as that. Then for the fixed moment at B, so we just use the same integrals. We just interchange the squared factor. So 2 plus x is now squared, 8 minus x is now raised to 1, then 9 minus x is now squared, x plus 1 is now raised to 1 on the next slide. So this is it. Fixed moment B equals negative integral 0 to 4, 3.75x plus 15 dx, 2 plus x squared, 8 minus x over 10 square, then minus integral 0 to 3 of 3x plus 21 dx times 9 minus x square, x plus 1 over 10 square. So the value of this integral is negative 89.92. The second is equal to negative 101.763. Combining fixed moment at B is the same as the results before in the first slide. So negative 191.683. So that's it for this problem.